Hello, welcome back to the stream. So in the past weeks, we've added structs. So in the past weeks, we've added structs. We're able to create structs, initialize them by accessing the members, and then get them, like printing them out again. So this part all works, but there are two features missing for structs. The first is the actual waste initializers, so you can do like initialize them here. And the second one, which is I think more important, is passing and returning structs from functions. So when we write a function print that takes an object of our struct, and then we just want to print each member out. So object.a, object.b, and then when we multiply this print f, this is not going to work. I'm actually curious what happens. Yeah, we're crashing. So the reason we are crashing is the following. Internally, like if I undo that code, no, we are crashing in code inventory. Okay. The lauf is a stack-based bytecode interpreter. What this means is then when we deal with values, for example, this 42 here, we push it onto the stack. So here we push 42 onto the stack. Yeah, 2a is 42. And what this means is that the stack where we push it on, it's 64 bits. So we can push 64 bits values into onto the stack. But if you can see here, the size of our struct is 16 bytes, or 2 times 64 bits. This is because ints are 64 bits, not 32. So they simply cannot fit onto the stack. And so normally when we call a function that, for example, takes a single int, we just push that int onto the stack and then have access on it inside the function. But for our struct, it simply won't fit. So we cannot pass the struct directly. Instead, we need to internally pass a pointer to the struct. And we are just not implementing that. So the naive code, we would just push the value directly, doesn't work. Instead, we need to synthesize storage for it, store the struct in that storage, and then push it out. So let's start by simply seeing why we are crashing and go from there. Okay, so we are creating variables for all parameters, but by generating a lauf type. And the lauf type is intuitively something that's like a first-class thing, but structs aren't that. If you have a decal type, we cannot generate a lauf type. So this is a null pointer right here, and this is why we're crashing. Okay, and this makes sense. Because what we don't actually want to generate the struct type here. We want to generate a pointer, because that's how the parameter is lowered. So what's the best way to start? So let's write a new function. So yeah, we've got layout. Let's name it like function argument type. Let's say the argument type. So codegen argument type. If it's an array, so if it's an array type, not bycast, I can use holds has kind. Then do I have unreachable macro? Yeah, unreachable. Array types cannot be passed to functions, right? So C doesn't allow that, so we don't need to worry about it. And if it's a struct, so this logic, then so if it's a decal type, for now we assume that it is a struct. To do, we assume it is always a struct. Since we don't have anything else, but if it's a type def, it would actually be fine. And I think the same is right here. Okay. Then we don't want to we instead want to pass a pointer. So so we return like the default type of a 64-bit value. So this is the this is the type of value stored on the VStack. So we return that, and otherwise we just code in the type itself. Okay. And so that's the idea. And then when we code gen function, not somewhere function body, yeah, code gen function body. We want the type, we want the code gen, the argument type. Let's actually call that parameter type. Okay, so now the calling function knows that it's getting a pointer. And it will store a pointer. Yes. But we actually then, the rest of the code probably, yeah. So then, like, if we actually look at that, so intuitively, we want to do essentially a transformation of this function to a function that looks something like so, object pointer on VStack, and then we want to do that. Create a copy. So we get a pointer on the VStack, and then we want to store a copy. And what this means is, so we've got, so actually we want to build a local that contains the entire layout of the type. The corresponding local variable should be big enough to contain the entire object. And the and then we want to store, actually I think this function is kind of useless because what we actually want is to do something like, if it's a decal type, regarding the echoes, I've turned the microphone a bit down, let me know if that helps. So if we've got the decal type, then, so if we are having a decal type, then we want to do something, otherwise we just use the type directly and store it as before. But if it's a decal type, rather if it's a struct, right here. Yes, so if it's a struct, then instead we want to mem copy it over. So we call built-in now lib memory copy, and the signature is destination address source. So we want the destination. So we want the destination on the stack, then the source address, and then the size. And we've got the parameter, so the source is on the stack, and we push the destination, so we need to do a swap. And then we want to get the size. curtain lauf layout type size, I think. Yeah, and this one is actually needed. So that should take care of the function side. So we've got our function print, and it creates a local variable to hold our struct. This is the struct parameter. And then we're getting, so it receives a single argument on the stack, which is the pointer to the struct. We're doing a bit of stack manipulation to essentially memcopy 9 bytes. Oh. I mean, yeah, I guess that's fine because it doesn't include tailing padding, but we don't need to copy padding. Okay. So we copy those 9 bytes over, and then we can just start using it normally and don't need to worry about anything else. So we just need to patch the call side now and clean up this code a little bit. So I'm using layout twice. Okay, so if it's a struct, the argument is a pointer to the struct object. We want to copy that into the local variable. Otherwise, the argument on top of the vstack, is the value directly. We want to store that into our local variable. Okay, so that's the idea. And now we need to adjust the call side. So the call side function call expression pushes each argument onto the stack. But in the case, what does it actually do when it's a struct? I don't know. Yeah, we are crashing somewhere when we... I don't actually know why we're crashing. Right here, we're doing a decay. Right. So the way the code looks right here is in... Oh, no, I don't have a call. So if we're having a call, we generate the address of the thing. So we get the address of the struct, and then we decay that by loading it with a decay expression. And what the decay expression does is it loads the value and puts it on top of the stack. And that doesn't work. But since it's a struct, we don't actually want the value. We want to get the address to pass that to a function. Decay for a struct also doesn't need to do anything. So at this point, the address of the L value has been pushed onto the stack. We need to load it if it's an object that fits onto the V stack. If it's a function, it's already the value. If it's an array, it's decayed from the address. If it's too big to fit onto the V stack, we don't actually... everything deals with pointers anyway, right? And then we can't put it loaded on top of the stack. So let's add a new function actually to generalize that, like the check that I've been doing for is it a struct? Bool is I can use this one is let's call it con fit onto low vstack. let's be fancy and call that its first class type. A first class type can be pushed onto the V stack and manipulated by Lauf directly. Otherwise, we need to use pointers and manipulate it indirectly. And it's a first class type precisely if CodeGen Lauf type does not return null. Yes. And then in our decay expression, we need to load it if it's a first class type. If it's not first class, and then I can do that. It's first class type, expression type. Okay, and then I can also use that when we do the body check right here. If it's first class type. Okay. Oh, right. The logic is reversed. And actually call print. Hey, and it works. Great. So we call at line 18. What this one is doing is it simply gets the address of the struct and then it calls print. And even though here in the call we have a decay expression that would push it onto the V stack, we added the special logic so we don't do anything and just push the address. And then when we call the function, it expects the address. It will copy it over and we can manipulate it locally. So that's really good. I just noticed since is first class type is like calls it and checks if it's not null, I can do that instead. And need to, if it's a first class type, adjust the comment logic, but that's passing structs as arguments. So let's commit that. Support structs as function parameters. Okay, the other half of the puzzle is returning structs from function. So struct foo make foo int a char b result that a equals a, result that b equals b, return result. Foo f equal make foo 11a. Right, unhandled non-scalar type. So we're hitting some to do and then nothing happens. Okay, so here's the same problem fundamentally. Normally the return value of a function is pushed on top of the VStack, but it simply doesn't fit on top of the VStack. So there isn't a lot we can do. Instead, we need to do another transformation, since we can't return a pointer to a local variable, right? Since it would be cleaned up. So we need to do a transformation that turns this function into one that returns void and takes a pointer as, let's say, first parameter. And then instead of return result, we do star output equals result. So this is the transformation that we need to do. And that way we don't need to put big things onto the stack. So first of all, we are hitting some to do in the compiler, which is interesting. What is this? Oh, it's the init one. That's something different actually. This is because this isn't an assignment, so the to-do will disappear now. Yeah, and instead we're crashing. Okay, that's more what I expected. Okay, so let's do the transformation. function. So first of all, when we declare a function, we are saying that if the return type is void, then we're returning 0, otherwise we're returning 1 value, and the parameter count is the number of parameters. This is incorrect now because we might want to add an additional parameter if it's not first class. So auto return counts. Let's use an immediately invoke lambda because it's getting a bit complicated. So the, let's say, return type is the return type of the decal. If the return type is void, then we don't return anything. Else if it's a first class type, then return 1. Otherwise, it's not a first class type. So add 1 parameter for the return pointer, parameter count, and return 0 since we don't actually return anything. Okay, let me wait this. Okay, so that's now the correct signature. And when we code in the body, let's say if it's the first argument is our pointer. So as given here, the first argument is actually the pointer. That means it's because it's a stack, it's after all other arguments. So at this point, we might have a pointer to store the return value. So let's create a local variable for that. So local, what's it called? Yeah. Return pointer. If it's the return type is not first class, what's it called? The decal, right? Then we want to save again the return pointer into a local variable, so we can access it easily. If we don't have a first class return type, we need to we get a pointer to write the result into. Need to save that to access it on return. Okay. So if it's not first class, we need to create a variable for it. Build local b love Adam type value layout. Get its address. And save the pointer into that. Okay, so now we are saving the pointer into the thing. And on the other end, when we have a return, somewhere I have a return statement. Right here. Right, so at this point, the expression has been visited and is on top of the B stack. Okay, so we might need to again do another mem copy into the corresponding pointer. So if it's not first class, which is if we have a return pointer, if the return type is not first class, on top of the B stack is a pointer to the object we're returning. Copy that into the requested pointer. Okay. So again, what we want to call is memcopy. We want to call memcopy. destination source count. So the destination is the whatever stored in our return pointer variable. Load. So we get the address of the return pointer variable. Then we load that one. So it's essentially the return pointer is a pointer to the storage location where we store the pointer that we want to write into. So it's a double pointer, so we need to do one load here. Type value 0. Then the source pointer is what's on top of the V stack. So we need to do another roll to get it. And then the size is uint. And then we get the layout of the decal type return type. And we want to copy size bytes. Okay. And that should deal with the like calls are not supported yet, but we okay. Wait, what? So inside print we are missing values. That's okay. What's going on here? Okay. So let's see. Make foo. It's a function that takes 3 parameters because of the hidden pointer and returns nothing. Then we do a bunch of parameter, like the first 3 allocations, like this one stores the pointer, then we've got the thing, A and then B, and then we create a result variable. We do a bunch of like save all the parameters right here. So we're so we're storing the uint 8, and then we're storing an int and a pointer. We are saving, setting the thing, and then line 5. This isn't line 15. This is line 12. Line 12, we get the address where we store a return pointer. Hang on, this is, oh, right. So this loads the result. So we load the address to result. We load the value that we saved, which is the return pointer. We do a swap to do the correct order for memcopy, and then we memcopy 9 bytes over. So this part appears to be correct. Now, what's going on with print all of a sudden? Why is print messed up? What's going on here? So we messed up the stack of print. So if the return type is not first class, in the signature, right, if it's a first class return type, then it's 1, 0. So let me see whether we compute the signature correctly. So make foo, we've already seen that has 3 parameters and no return type. Print has 1 parameter and 0 return type. So that part is correct. So we should hit this part only 1, but we are hitting it twice. Oh, right. So the issue is that void isn't first class either. So if it's not void, So if the return type is not void and not first class, only then do we have an actual pointer. Okay. Okay, now that part still works. Okay, so let's look at the other end again, which is the function call. So the function call is we are pushing argument onto the stack. But if it's not a first class return type, then we actually need to create some value where we can store the result into. So let's handle that first. So we get the type. So if, again, if it's not void, and it's not first class, then we need to generate space to store the result into. We need this. Let's call it call result. Call result is local, what's it called, build local. So we create a new local variable big enough to store our thing. And then we push its address onto the vstack. Okay, and then we push each argument, then we call the function. Right. So this one needs to be manipulated right here. So we have an extra argument. And the return code is 0. Then we call the function. And finally, at the end, we need to, like the other code expects that the function pushes the result onto the vstack. But since we can't do it, if it's not first class, we still need to push its pointer. So if it's not first class, we need to push the pointer onto the vstack. So, and this can be set. So if call result is null, then we just want to get its address, because this is where the result is stored. Okay, and now that should be enough to make this one work. Okay, almost. Right. Right, when we do a store. Okay, so the issue actually here is so this part works. Line 24. Line 24 right here. So we've created a local variable to store the call result. We push its address onto the stack. We push 11. We push A. We call the function. And then we should get its address onto the stack. Oh, right. Then we get the address onto the stack, but since we are like discarding it, this has been constant folded away. But in principle, we are pushing the address onto the stack. Now the something like that should work. Okay. One thing at a time. Okay, so let's handle that later. What this assertion right here is about is that assignment does a store operation, but if it's not first class, it cannot do a store operation. Instead, we have to do a mem copy. So if we're having a type we can store it. Otherwise, we need to mem copy into the address. Okay, so we've got the address on the L value into the stack, so we need to do, let me guess, I think we need to do a swap. So we do a swap, and then we need the size. Layout. And then we can do another mem copy. With memory copy. Hey, now that part works. So, and the assignment right here in line 24. So we call the function. Then we get the result of the call, which is the pointer to the variable where we stored the thing, which is local address 1. We push, and then we want to store that. So we need to call memcopy, and for that we need to get the destination as well, swap the two in the correct order, get the size, and memcopy it over. And then we just pass the pointer to print, which will then extract the necessary things. And we are printing 11 and A. So that part works. Before I commit that, note that, like, we're calling the function, where is that? So we're calling the function, and then we expect to get the result, which we manually needed to push again. I think it's more elegant if the transformation, so currently we're doing, as discussed, we're doing this transformation, where we're returning void. So we get a result pointer, and then we do a mem copy for that, and then return void. I think it's more elegant if we instead return then the result pointer, and then we don't need to like push it again onto the stack because the call does it for us. I think we can simplify a bit of logic here if we do that transformation. So what this means is when we declare the function, actually we still want to return 1. We return the return pointer from the call. When we do the return statement, evaluate to the address of the return pointer instead. Not to the address, to the return pointer instead. We know how to get that. Okay. And then when we have the call expression, we don't need to push the pointer onto the v stack because the call does it for us, and we don't need to reset the return count. And if I did everything correctly, this part should now work. Yes, so the same deal. And just instead of our make function, now just returns, hang on, I know 2 make functions. Hey, shouldn't that generate an error at some point? Apparently we are accidentally allowing overloading in C, which isn't something that should be okay. Okay, so the make foo function takes 3 arguments, the pointer and the actual one, and then we return 1. And then finally we, like when we call it, we get the pointer as well. Okay, so the call side just calls it and doesn't need to load it separately, which is a bit nicer. So let's commit that. Support structs as return values. What was the previous commit methods? Ah, yeah. From function, okay. Okay, now there are a couple of bugs. So this one doesn't work. Right. Why do you not want to work? So we codegen an L value, which is our object. Oh, right. So we're codegening an L value, which is a function call, right? Which is not true. So when we evaluate the member access, we need the address of the object. Evaluate, get the address of the object and put it on top of the stack. Right. So we're calling codegen L value, which evaluated, i.e. we get a pointer. So normally a function call would not be an L value. But in this particular case, when we're doing a member access, we have the address of the thing, since the left-hand side of the member access is a struct which will not fit onto the vstack, like even if it's small, let's say, and then we always have an address. But it's still not an L value, so let's rename it codegen address as a pointer. And this is possible when we have a function call that returns a struct. Function call. I wonder whether that's, let's special case it in the caller instead. I think that's nicer. So if it's, yeah, since we don't want to actually, so we can just codegen it's normally not as an L value. Since it's not a first class, we will always get the address anyway. Since that's the only way we can manipulate it. Get the address. Since it's a struct type, which is not first class, the result of the expression will be a pointer anyway, even if we don't evaluate it as an L value, since decay does nothing. Right. Okay, so now that part works. Fix member access on call result. Okay. Let's look into the fact that we apparently allow overloading. What happens if I do that? Yeah, so something doesn't like redefinitions. We're simply not catching them. So somewhere insert new decal. Right, if both are definition, then we should, why are we not reaching this part? Like, that's a bit odd. Let's see. Okay. Okay, so now we've got something, a decal, and we've got a shadow decal. Okay, and they're not the same pointers. Shadowed is a definition, so we're shadowing an existing definition. Aha, but we're not, maybe we are not a definition. Oh, we're also doing structs, that's fine anyway. Okay. Let me set the breakpoint in the appropriate place. Shadowed decal. Shadowed is definition. Decal is definition. Still a struct. Okay, now we have function decal. Right here. Okay. So when we insert the function deckel, it does not get a definition. So, right, because it's not always a definition. Can I? Right, so we unconditionally want a body, so we know that at this point it is a definition. So we make it a definition, and then the shadow warning should trigger. Yes, duplicate global definition. Okay. And this should happen like regardless of signature, because we don't actually have overloading, yes. But I think this code is still fine. Oh, it is not. Like, I'm really surprised that we catch that. I can probably confuse it. Invalid declaration specifier for function? Really? That doesn't seem right. Oh, I think we just don't allow static function at the moment anyways. Okay. See, catch duplicate function definitions. Do we allow static functions? Static void foo? Apparently not. Invalid. What's the other message? Invalid declaration specifier. Invalid declaration specifier for function. If the type spec is valid for function, which is the linkage. Oh, right, because it has a storage duration. Right. Because static does two things. It sets the linkage to intern, and it sets the storage duration to static. And functions don't have static storage duration, since they're functions, but they do have linkage. But static sets both. So it's valid if functions need linkage and either the storage duration is empty or the storage duration is static. And okay. And now we should allow static functions just based on that check. To allow static forward declarations as well. Okay. Allow static functions. And they do have, yeah, internal linkage. Okay. That's good. Okay, we were a bit sidetracked. Let's continue with structs. So something that's a bit annoying is if we do the following. Result.a equals A, result.b equals B, return the result. So the bytecode, like we create a bunch of local variables, we store it in there, and then we mem copy it over. And if we now do something like this, make foo 0, 0, then what's happening in this bytecode is we are creating a variable to store the result. So we're getting a pointer to store the result into. We are calling foo with that pointer and our parameters. We are getting the result back, and so copying it in. And essentially what's happening is, if we consider the lowering, so we've got make foo, which takes our foo pointer, JRB does something, and then we set f to result. And then in forward, it gets another pointer, calls make foo, so we create a temporary call makeFoo, and then do that. And what we could have done instead is that, right? Since we are returning, we can just store the pointer directly. This is essentially the same issue that C++ had with copy elision. So when we do have a return statement like so, we don't actually call a copy constructor. Instead, we forward it directly to the correct location. And this is something we can also do here, right? So instead of creating a temporary, passing it, having makeFoo populate the temporary, and then memcopying the temporary over, we can just detect that and pass the pointer in directly that we want to return. So let's try and implement that. So let's add a test for f. F is forward, and then we want to print f.a and f.b, and let's use interesting values right here. So the code still works, but it does, let's count the mem copies. So we're doing 1 mem copy, 2 mem copies, 3 mem copies. So we're doing 3 mem copies just to get our struct. So let's try and bring that down. So if we're having function call, oh, not compiler, inclusion. So if we're having a call expression, then we create a temporary to store our result into. And then we use that. Now, in the case of return foo, we don't need to create a temporary, we can just return our result value instead. So why not have the following? So if we're having a function call expression that's a child of a return, we don't need a temporary, we can just get the pointer directly. And what this means is, let's say we create encode an expression, we pass in a new argument. Let's call it the so it's a local variable. No, it's not a local variable. Is it a local variable? Yes, it's a local variable. Let's call it the result pointer. So to code an expression, we need to pass in a result pointer. And in the case of a function call, if we are having a result pointer, then we use that. Otherwise, we create a temporary, right? So now we can reuse that result pointer. And if we have one, and what's left to do is just pass that around to all the calls. So, okay, let's actually make that a bit nicer. We're dealing with a return type that is not first class. So we need to push pointer to store the result into. If we're having a result pointer, then we use it. If we have a result pointer, we can just use that one. Else we need to generate spades to store the result into. And implicitly here, the precondition is that if we provide a result pointer, it must have the matching size. Push the address of the moment, is it the local? Oh, okay. Yeah. Push the address of the local we want to store it in. And actually it's not really a result pointer, because it's not a pointer to the result, it is the result storage. Okay. And implicitly here, the precondition is that if we provide the result storage, it has the appropriate size. But that's the job of the caller. And let's see, right here. Let's just follow the compilation errors. Let's actually make it easier, since we are only having it in one place when we do a return. So this one should still work. We're just still having our 3 mem copies. So make foo does a mem copy, and then forward does another mem copy. But now we can use the return statement. Right. So when we enter a return statement, actually we can, we need to manually visit the, okay, so we need to manually visit the return statement. Generate code for the return expression, passing it the result storage. Code gen expression context the expression, which is our return pointer. Oh, okay, so now we're having a type mismatch. So at this point we're having a return pointer, which isn't the thing. So we do have a storage. Okay, so this isn't the result storage, this is the result storage pointer. After all, so it's a local variable that stores a pointer to the thing we want to write the thing into, which means that here we need to do that. Right, and I don't actually need call result afterwards anymore, so instead we need to just load it. Result storage pointer. Okay, let's see what happens. Okay, so we still got the correct results. Did we have fewer mem copies? No. Doesn't appear to be that way. So we still got 1 mem copy here, 1 mem copy here, 1 mem copy here. Okay, so did we actually trigger this case? We did. Oh, right. We don't actually save on mem copy. Wait, why are we not saving on mem copies? So we directly generate so the optimization forward is what we're dealing with. Oh. So what is forward doing? It gets a pointer and it stores that, and then it calls make foo with. Oh right, but we are calling, so we don't generate a temporary, but we're. What is the mem copy doing? Function call. Like, who's actually generating the mem copy at this point? Maybe the return. Oh, I think. Right. So we don't need the mem copy. So this code is generating the mem copy, even though this is not necessary, since we passed in the return pointer and directly written it to the return pointer. But not every expression writes the result to the return pointer. It may just be on top of the v stack. So if the return pointer is not, so if we know that we are having a call, that's a bit ugly, has kind seed of function call expression, then we don't actually need the mem copy. If it's a function call, we don't need the mem copy, since the function will populate return pointer. Okay. Right. So we don't actually need the entire thing. Right. So we still get the correct values, and forward doesn't do a mem copy. So that's copy elision. Instead, we're just saying make foo, please get the value and use the return pointer that was passed to us and store that in there. So that's really cool. Okay. Let's commit that part. Add basic copy elision when returning function result. Now, C++ also has the named return value optimization, which would happen in case of make foo. So it detects that result is a local variable that is returned. And since we always, and in this case, we're always unconditionally returning result, we can just use the pointer that was passed in directly instead of creating a local variable. But this requires non-trivial analysis to do, because it works in this case. But if we, let's say, have something like result, otherwise result 2 or something, and then we have another local, then we cannot elide them both if we need them at the same time. So this requires like some analysis, which is not trivial to do. So let's not do that right now. But we can handle it in this case right here. So in the assignment, what the lowering is doing. So this one gets translated into struct foo temp, forward temp, f equals temp, right? Since we're creating a temporary for the call, we store that in there and then we mem copy it over. And we can do another case of like elision by lowering it instead to forward and just write the result directly into temp. So let's try that. If we are having an assignment expression, we essentially doing like a mem copy in here, right? And instead we want to build the thing. So if we're having an assignment of and the right hand side is a function call and the type is non-trivial, then we can do elision. Otherwise, we still need the correct store. Although we could like globally change codegen expression. So currently, since we don't necessarily, it's also not, so we want to, like, it expects us, like currently codegen expression expects that we get a local variable that holds a pointer, and we want to store it into the pointer that is stored in that local variable. And in the case of assignment, we want to store it into the left-hand side operand, which is not stored in a local variable. So that's a bit tricky to do. Right, since we can't, like, we don't have a local variable that we can pass in and say, hey, this local now holds the address that we want to store it in. What we could do is, so there are two approaches. The first one is we completely change the entire codegen expression and say that instead of like getting a value, since we ultimately we want to store the value somewhere, right? All expressions in C, like we want to do something with the value. So there are essentially three things. We want to evaluate an expression and store the result, or we want to evaluate the expression and discard the value, or we want to evaluate the expression and then we want to do like a branch decision. And only in the last one do we actually not ultimately store the expression somewhere in memory. For everything else, it will be stored in memory. So we could generate like a new kind of like change codegen expression. So it will always store the expression into the address, let's say that's on top of the V stack, instead of just leaving the address on top of the V stack. Yes. And then we can get a bunch of things. And the other approach would be to just special case the case we are assigning a local variable with a function call. And then we can just special case that in here, but that's a bit ugly. I think the structural change is definitely the way to go if we want to support that sort of optimization. But I don't think it makes sense to start that right now, because it would require like refactoring the entire expression codegen, and I've already been streaming for an hour, so yeah. So I think let's just end the stream right here for today, and we will definitely continue working on that next time. I think like the already copy edition that we have is quite cool. So thanks for everybody who stopped by. Hope you enjoyed the stream, and until next week.